Welcome to the 10th lecture on Module 1 of the Fluid Machinery course. In the last session, we derived expressions for the runner power, hydraulic efficiency, maximum hydraulic efficiency, and also the condition for attaining the maximum hydraulic efficiency in case of a Pelton turbine. Objectives of this lecture is to discuss the design aspects of a Pelton turbine. Designing a turbine basically means we have to arrive at the dimensions of the turbine from the given requirements. That is the shaft power requirement, overall efficiency, a net head available for producing useful work, then the discharge or flow rate handled by the turbine, then the rated speed or the rotational speed of the runner in RPM, N, etc. So from the given parameters, we have to arrive at the diameter of the turbine runner. In this case, the diameter of the Pelton wheel, and the jet diameter or the nozzle diameter, small d, the number of jets, say n, dimensions of the buckets like axial width of the hemispherical bucket or radial height of the bucket and depth of the bucket. So we will come to that shortly. Then number of buckets to be mounted on the periphery of the Pelton wheel. Consider this layout of a Pelton turbine. A typical Pelton turbine installation can have a schematic layout like this, and you have the reservoir, and the water level in the reservoir is indicated by the head race, and this is the penstock pipe taking water from the reservoir to the power station where the turbine is installed, and after the extraction of power, the water is discharged to the region what we call tail race, and the water level in the tail race is indicated by this. The vertical height difference between the head race and tail race water levels is known as the gross head, usually denoted by H suffix G, and the net head available at the turbine inlet to produce useful work, that is indicated by net head, denoted by capital letter H. There will be a head loss during the flow of water through the penstock. Let us denote it by H suffix F. So HF is the frictional head loss during the flow through the penstock. And how do you find out this loss of head due to friction? HF. And that HF can be found out by Darcy-Weisbach equation. The relevant terms which you have to keep in mind is gross head, that is the vertical height difference between the head race and the tail race water levels. Net head, capital H, that means it is the available head at the turbine inlet for producing useful work. From this diagram, if this HF is indicated by this height, then the net head available at the turbine inlet for producing useful work is given by H is equal to Hg minus Hf. You are already familiar with the term hydraulic efficiency, and that is one of the stage efficiencies of a turbine. And then we can have mechanical efficiency, and collectively, while referring to the overall output and overall input to the turbine, then we can have an efficiency rating called overall efficiency also. Net available head for producing useful work, capital H, that is equal to Hg minus Hf, where Hg is the gross head in meters and Hf is the head loss in penstock due to friction, that also in meters of water. And this Hf can be found out by Darcy's equation, and you may be familiar with that. Hf is equal to 4FL V square by 2G D, where F is a Darcy's coefficient of friction, L is the length of the pipeline, then V is the average velocity of flow through the pipeline, then D is the diameter of the pipe, and G is the gravitational acceleration. and in this case we are going to consider the frictional head loss in the penstock pipe. So that will be equal to 4F LP Vp square by 2G D suffix P. Here the suffix P in the case of length L, that is length of the penstock, L suffix P. V suffix P, Vp is the average velocity of flow of water through the penstock, and D suffix P is the diameter of the penstock pipe. Remember, 4 times F can be considered as the Darcy's friction factor also. Now consider this, the head available with water at the inlet to the nozzle, that is this capital H. After passing through the nozzle, what happens is the entire energy associated with water is converted to kinetic energy. So that means the velocity head of water coming out of the nozzle as a jet, that is V1 square by 2G. And that V1 square by 2G is equal to the net head available H. Therefore, theoretically, H is equal to V1 square by 2G, considering that there will not be any energy losses in the nozzle. The theoretical velocity of the jet V1 is equal to root of 2gh, and the actual velocity is equal to Cv into theoretical velocity, that is V1 actual is equal to Cv into root of 2gh, that much meter per second, and Cv is the coefficient of velocity of the nozzle that takes care of the losses in the nozzle. Usually the value of Cv ranges from 0.95 to 0.99. For a typical design case, you can assume the value of Cv as 0.98. We already know that the tangential velocity of the wheel or the velocity of the buckets at inlet and outlet, they are same, and that is equal to pi dn by 60. In the case of Pelton wheel, we know that d1 is equal to d2 is equal to, say, common diameter d. And here from this diagram you can understand what is d. In this diagram, the diameter of this circle represents the effective diameter of the Pelton wheel, or it is also known as mean bucket diameter. The nozzle central line is represented over here. The circle that is representing the mean effective diameter, that circle is tangential to the nozzle central line. Consider the diameter of the jet as small d, and area of the jet, we know that it is equal to pi by 4 d square, and now number of jets, we can consider this as n, and discharge through one jet, let us represent it by small letter q, that is equal to area of the jet multiplied by the velocity of jet, actual velocity. So area into V1, that is pi by 4 d square into V1, and that is small letter q, that is discharged through one jet. In case of Pelton wheel with multiple jets, then the total discharge handled will be q, capital letter Q, that is equal to n into small q. Is number of jets multiplied by discharge through one jet. Therefore, Q is equal to n into pi by 4 into small d square into V1. In order to distribute the total discharge that is fed to the turbine, so we will make use of multiple jets. Now, what is the use of multiple number of jets? If you want to increase the power developed in a Pelton turbine, the suitable option is to use multiple number of jets rather than using a single larger jet. So we can have number of jets striking the same Pelton wheel runner. So that will reduce the size of the bucket and size of the Pelton wheel. Practically for large hydropower stations employing Pelton turbine, we can have number of jets as high as 5 to 6. Here we have this diagram with a Pelton wheel that is fed with water by 5 jets. And we know that Pelton turbine is known to be a high head turbine and comparatively low discharge, lower discharge compared to the reaction turbines. Two important ratios for the Pelton wheel. One is jet ratio and other one is speed ratio. And jet ratio, let us denote it by small letter m, that is equal to d by d, capital D by small d. Capital D is the effective diameter of the Pelton wheel and small d is the diameter of the nozzle or diameter of the jet. And this jet ratio is usually kept in the range of 10 and 16 for better performance. And now the second ratio is speed ratio. Speed ratio, we can denote it by K suffix U, and it is connected with the tangential velocity of the wheel. So that's why K suffix U. So K suffix U is equal to U1 divided by root of 2GH if the speed ratio is based on inlet tangential velocity of the wheel. But in the case of Pelton wheel, U1 is equal to U2 is equal to U. So you can simply write KU is equal to U divided by root of 2GH. So usually speed ratio for a Pelton wheel ranges between 0.43 and 0.48. For practical purposes, you can assume a speed ratio of 0.46 for our analysis. Now already we know that the best bucket speed, that is for maximum hydraulic efficiency, we can write U optimum, that is equal to V1 by 2, or V1 is equal to 2U is the condition for maximum hydraulic efficiency. So therefore the best bucket speed, if you want to calculate, that will be equal to V1 divided by 2. Now how many buckets are to be used? There are many empirical relations, and one such empirical relation to find out the number of buckets, let's denote it by Z, is equal to 0.5 times the jet ratio plus 15. That means 0.5 into that capital D by small d ratio, that is called jet ratio, plus 15. For example, if the jet ratio is 10, then 0.5 into 10 plus 15 will be the number of buckets, that is 5 plus 15, 20 buckets if the jet ratio is taken as 10. And we already discussed the jet ratio ranges between 10 and 16. Now we consider the bucket dimensions, the hemispherical vanes mounted on the Pelton wheel runner. See, one such bucket is shown over here, and this is the width of the bucket. Actually, that is the axial width of the bucket. And this bucket dimensions are specified in terms of the diameter of the jet, small d. So usually the axial width of the bucket, that is this dimension, so that is taken as 3 times diameter of the jet to 4 times diameter of the jet. That is 3d to 4d, that is the axial width of the bucket. Now the radial height, that is when this bucket is mounted on a wheel, this height means that becomes the radial height. So the radial height of the bucket, that becomes 2 times the diameter of the jet to 3 times the diameter of the jet. That proportion you should remember. Then this hemispherical cavity, that is the depth of the bucket, inward depth, or it's more clear from this diagram. So the inward depth of the bucket, that is taken as 0.8 times diameter of the jet to 1.2 times the diameter of the jet. Axial width of the bucket, that is this length, as 4 times d, and the radial height, that is this length, that can be taken as 3 times d, and the depth of the bucket as 1.2 d. Now we will discuss the various efficiencies of a hydraulic turbine. Consider this diagram. So I have indicated 1, 2 and 3. Here stage 1 is the turbine inlet. So the power associated with water at stage 1, that is water power. and that is given by rho Q G H, where H is the net head, Q is the flow rate or discharge handled by the turbine. Now stage 2, that is the runner. So after transferring energy to the runner by this water jet through the impulse action, so we will get runner power, that is by the work done by the water jet on the runner per second. So that is known as runner power. Runner power is equal to rho Q G H suffix E. H suffix E, that represents the runner head or head impressed by water on the runner. That is a theoretical head. HE is equal to VW1 U1 minus VW2 U2 divided by G. VW1 and VW2 are respectively the world components of velocity at inlet and outlet of the vane, and U1 and U2 are the velocity of the vane at inlet and outlet. U1 and U2 are the velocities of vane at inlet and outlet, which in the case of Pelton wheel, they are equal. U1 is equal to U2. For a Pelton wheel, the Euler head HE is equal to VW1 minus VW2 into U. So this U can be taken out. So VW1 minus VW2 in a bracket multiplied by U divided by G, that is the Euler head. Obviously, Euler head is less than the net head available at the inlet H. So if you consider the stage 1 and stage 2, so what happens between these two stages? So there will be some hydraulic power losses, and this hydraulic power losses will be equal to water power minus runner power. And now you consider stage 3. See, stage 3 means that is the runner shaft, the shaft on which the runner is mounted, and from that shaft we will get useful mechanical power. So the useful mechanical power that is available at the runner shaft, that is called shaft power. So shaft power, generally represented by capital letter P, is equal to the torque available at the shaft multiplied by the angular velocity. See, when you consider stage 2 and stage 3, stage 2 power produced is runner power, and at stage 3 we have shaft power. That is the overall output from the turbine, and overall input is the water power. So if you consider stage 2 and stage 3, there will be mechanical power losses. So that means runner power minus mechanical power losses will be equal to shaft power. So as we proceed from stage 1 to stage 3, progressively the available power decreases from water power, which is greater than runner power, and that is greater than shaft power. If you consider the overall output power and the overall power input, that is stage 3 and stage 1, then you will get overall power losses, that is the sum of hydraulic power losses plus mechanical power losses. So if you consider an efficiency rating between 1 and 2, then you can have hydraulic efficiency. So hydraulic efficiency is the ratio of runner power to water power, that is 2 by 1 in this case. And if you consider stage 2 and stage 3, we can have an efficiency rating known as mechanical efficiency, because that takes care of the mechanical power losses. So 3 divided by 2, that is a power at the stage 3 divided by power at the stage 2, shaft power divided by runner power, that is mechanical efficiency. For example, hydraulic efficiency, if it is equal to 90%, that means there is 10% hydraulic power losses. So if the mechanical efficiency is 85%, that means there is 15% of mechanical power losses. See, the overall efficiency now, that is shaft power divided by water power. So overall efficiency of any turbine is the ratio of shaft power to water power. That is 3 divided by 1. So obviously 3 divided by 1 is equal to 3 divided by 2 multiplied by 2 divided by 1. If you take the product of mechanical efficiency and hydraulic efficiency, that is 3 by 2 multiplied by 2 by 1, obviously you will get 3 by 1. So that means if you take the product of the two stage efficiencies, mechanical and hydraulic, then you will get overall efficiency. Now along with the design aspects of the Pelton turbine, we should provide the information related to the velocity triangles of the Pelton turbine also. So always while giving the details of the design aspects of a Pelton turbine, you should give the velocity triangles for the Pelton turbine also, which we discussed already. Now having completed the discussion on the design aspects of the Pelton turbine, now we will proceed and solve a numerical problem related to that. Question is this: a Pelton turbine is required to develop 6 megawatt when working under a head of 300 meters. It rotates with a speed of 500 rpm. Assuming jet ratio as 10 and overall efficiency 85%, calculate diameter of the wheel, then quantity of water required, number of jets and specific speed of the turbine. Assume the required missing data suitably. So here shaft power is given. The turbine is required to develop 6 megawatt. That is a shaft power denoted by, let's say, capital P. That is equal to 6 megawatt. That is 6 into 10 to the power of 6 watts. The net head here is H is equal to 300 meters. That is the available head at the inlet of the turbine for producing useful work. So capital H is equal to 300 meters. And overall efficiency is 85%. See, the rotational speed of the turbine N is given 500 rpm. And the jet ratio is given as 10. What is jet ratio? That is diameter of the wheel divided by diameter of the jet. So capital D by small d, usually denoted by small letter m, that is equal to 10. Capital D is the effective diameter of the Pelton wheel. Small d is the diameter of the jet issued by the nozzle, or diameter at the outlet of the nozzle. So capital D is equal to 10 times small d, or small d is equal to capital D divided by 10. Now, in order to proceed further, we require a data to be assumed. That is the speed ratio of the turbine. Because here we are asked to calculate the number of jets. So that means possibly this could be a case when the number of jets is more than 1. So therefore, unless we have the speed ratio, we will not be able to proceed ahead. So we will assume a speed ratio of 0.46. I already told you that speed ratio is denoted by KU, that is equal to U divided by root of 2GH, and the value of which ranges usually between 0.43 and 0.48 for the Pelton turbine. And let us assume the speed ratio to be equal to 0.46. So therefore, KU is equal to U divided by root of 2GH, which is equal to 0.46. So therefore, U is equal to 0.46 into root of 2GH. Here the net head H is given 300 meters. So now you are in a position to find out the tangential velocity of the wheel. So U is equal to 0.46 into root of 2 into 9.81 into 300. So the velocity of the bucket, or tangential velocity of the runner, which at the inlet and outlet are same, that is equal to 35.291 meter per second. Now how to get the absolute velocity of the jet? V1, and V1 is equal to CV into root of 2GH, that is the actual absolute velocity of the jet at inlet. And since the value of coefficient of velocity for the nozzle is not given, CV also you can assume. CV can be assumed as 0.98. So V1 is equal to 0.98 into root of 2GH. So 0.98 into root of 2 into 9.81 into net head is 300. So absolute velocity of the jet at inlet V1, that is actual velocity, that is equal to 75.186 meter per second. Now, from the tangential velocity of the wheel, that is u is equal to 35.291, now we are in a position to find out the answer to the first part, that is diameter of the wheel. So u is equal to pi dn by 60. So from that we can find out the diameter is equal to 60 times u divided by pi n, that is 60 into 35.291 divided by 500 pi. So the RPM n is given as 500, the rated rotational speed of the runner in RPM. So the diameter d, that is the effective diameter of the Pelton wheel or mean bucket diameter, so that is 1.348 meters. That is answer to the first part. Now let's proceed ahead. See, the diameter of the jet, that is equal to the diameter of the wheel divided by 10, 1/10 of the diameter of the wheel, because the jet ratio is given as 10. We discussed it already. So small d, that is the diameter of the jet, is equal to the diameter of the wheel divided by 10, 1.348 meters divided by 10, that is 0.135 meters or 13.5 centimeters. Now we will proceed and find out the quantity of water required. So what does it mean? That is actually the flow rate required. We will be able to provide the flow rate. So much meter cube of water every second is required by the turbine to produce the 6 megawatt power. So the overall efficiency, that is eta naught, that is equal to shaft power by water power. Shaft power is P divided by the water power is rho Q G H. So what is Q? So Q is equal to P divided by overall efficiency into rho G H in the denominator. So the power must be in watts, because rho Q G H, if you substitute Q in meter cube per second, G in meter per second square, H in meters, and rho in kilogram per meter cube, rho Q G H, the water power you will get in watts. Therefore, the numerator also must be in watts. So the power in watts, that is 6 megawatt converted into watts, 6 million, 6 into 10 raised to 6 watts divided by 0.85, that is overall efficiency. The density of water 1000 kilogram per meter cube, gravitational acceleration 9.81 meter per second square, and H is net head 300 meters. So once you do this, so you will get Q. The discharge of 2.3985 meter cube per second is the answer to the second part of the question. Quantity of water required every second. So now the discharge Q, that is the total discharge, is equal to number of jets multiplied by discharge provided by one jet. So n, small n represents the number of jets multiplied by small q, that is the discharge provided by one jet, that is n into pi by 4 small d square into V1. So we know these quantities, and you can find out the number of jets now, because number of jets n is equal to capital Q divided by small q, the total discharge divided by discharge through one jet. So now discharge through one jet is small q, that is pi by 4 small d square into V1, pi by 4 into small d is 0.135, that squared into actual velocity of the jet we found out already, 75.186 meter per second. So if you multiply this if you take pi by 4 d square, you will get the discharge through one jet as 1.0762 meter cube per second. See, this discharge provided by one jet is 1.0762 meter cube per second, that is more than 1000 liters per second. And now number of jets, capital Q divided by small q, that is 2.3985 divided by 1.0762. So you'll get 2.23. So it cannot be a fraction since you are considering the number of jets. So you cannot take the lower value out of this because that will not be sufficient to produce 6 megawatt power. So therefore you take the next whole number. Number of jets in this case is 3. Now number of buckets. See, we have already discussed there is an empirical relation for finding the number of buckets. Number of buckets, let's denote it by Z, is equal to 0.5 times the jet ratio plus 15. 0.5 times the jet ratio here is 10. That is a capital D by small d ratio. Plus 15. So that is 5 plus 15, that's 20. So number of buckets required to be mounted on the Pelton wheel in this case is 20. Now the other dimensions of the buckets. See, usually the buckets dimensions we will express in terms of the diameter of the jet. So diameter of the jet in this case is 0.135 meters or 13.5 centimeters. So width of the bucket, that is axial width of the bucket, you are familiar with that dimension already. So axial width of the bucket in this case, you can take it as 4 times the diameter of the jet. 4 times 0.135, that is 0.54 meters or 54 centimeters. Then height of the bucket, that is radial height of the bucket, is equal to 3 times the diameter of the jet. You can take this proportion. So 3 times 0.135. So that is 0.405 meters. Similarly, one more quantity is missing here, that is the depth of the bucket, inward depth of that hemispherical bucket or hemispherical cavity. So that you can take it as 1.2 times the diameter of the jet. So you can take 1.2 multiplied by 0.135. So whatever you get, that much meters, so that will be the depth of the hemispherical bucket. And now the final part of the question, that is specific speed of the turbine, denoted by capital N suffix S. So we are going to deal with this topic in detail in the second module. But for time being, since that is a part of this question, so I will tell you how to find out the specific speed. So the specific speed of the turbine is given by the expression n root of P divided by h raised to 5 by 4. We have to derive this expression also. We have to derive this expression also later, but for time being, you please keep in mind specific speed ns is equal to n root of P divided by h raised to 5 by 4. N is the rotational speed of the runner in RPM, but more importantly, you should remember power, this P is the shaft power in kilowatts. So if you want specific speed in SI units, then the power, the shaft power in the expression for the specific speed must be substituted in kilowatts. So the power here, the shaft power is 6 megawatt, which of course is 6 million watts, but in kilowatts it is 6 into 10 raised to 3, that is 6,000 kilowatts. So that 6,000 you have to substitute here because that shaft power must be in kilowatt in this expression. So the rotational speed N is 500 into square root of 6,000 divided by net head h, that is 300 raised to 5 by 4, that is 1 raised to 1.25. So what do you get? The specific speed is 31.02. It is not dimensionless, it has a unit but not RPM, it's a complex unit. So let us present like ns is equal to 31.02. This is a specific speed of the given Pelton turbine. Actually, the range of specific speed reveals some other ideas also. So if the specific speed of the turbine ranges between 30 and 50, that obviously means it is a Pelton turbine with multiple jets.